Hello everyone, myself Pushpendra Kumar. Today now I am presenting the part A of assignment 1 of the solid state CML 661. In this part, we will discuss about the morphology and the point group of the crystals we have that is given in the class. So let's start. These are the these are the images which are taking from the different views and different angles. So different types of the images are there. From here we can say that these are the three different axes, three different lattice parameters of these crystals, and these are the angles between these lattice parameters. We can see here that A not equal to B. Here we can see that A is not equal to B and not equal to C. So because A is the larger than the B and C is larger than the B. So from the diagram we can see that A not equal to B and not equal to C. And here we can see the angle between the A and B, which is known as the gamma angle, which is known as the gamma angle is approx 90 degree, and the angle between the B and C, which is known as the alpha angle or the 90 degrees, all about the is approximately 90 degree. And from uh, diagram we can see that the angle between the A and C, which is the beta angle, is not equal to the 90 degree. It is larger than those angles between the A and B and B and C. So from here we can see that A not equal to B and not equal to C. And also the angle alpha and gamma are 90 degree, but beta is not equal to 90 degree. So, and this crystal is also shows that from this crystal we can also say that this crystal shows the prismatic habit elongated along the b axis. It's like a elongated prism along the b axis, uh, and here we can, if we rotate 180 degree along b axis, then we get the same crystals. So from here we can see that here, C2, a two-fold axis of rotation also present or also appear. So from here we can conclude that since the A not equal to B not equal to C, alpha equals to gamma equals to 90 degree, but beta not equal to 90 degree. So from here we can say that this crystal lattice parameter corresponds to the monoclinic structure. These lattice parameter corresponds to the monoclinic structures. So here we can say that the crystals given in the class corresponds to the monoclinic system. Now move towards the point group of this system of the crystals lattice. From the Harman-Magnin notation, we can see that for the monoclinic system, there may be the point groups like 2 star or 2 by m or m. Since there is a two-fold axis of rotation and there is also a mirror plane, and there is also a mirror plane. So from here we can say that this crystal, we can say that this crystal corresponds to the M2 by M crystallographic point groups. So the point groups of this crystal given in the class is the 2 by M, and this crystal corresponds to the monoclinic system. So thank you. It is all about the lattice, the crystal. Hello everyone, myself Pushpendra Kumar. Now I am presenting part B of assignment 1 of solid state CML 661. In this part, we will discuss about some crystal structures and the ferroelectric behavior of BaTiO3 crystal on applying the electric field. So let's start. So first crystal is the calcium telluride structure. First is the calcium telluride crystal. So this is the it is a rock salt type structure in which calcium ion form the abscissa lattice and tellurium atom form the present in the octahedral void. Since it is forming the FCC, so calcium ion will be present on the face center, 6 face center or plus 8 corner. So from here we can find the number of the so these are the calcium atoms which are present at the corner and the face center of the cube. We can find out the number of the calcium atoms in one unit cell. So 6 faces and contribution at each face is 1 by 2 and 8 faces and the contribution at each corner is 1 by 8. So from here we can find out the number of calcium atom is 4. So number of calcium atom per unit cell is 4 and due to the neutralization we have required number of calcium ion and number of tellurium atom will be equal to same. So number of tellurium atom per unit cell is also equals to 4. The cell parameter, since this is a cubic unit cell, so the cell parameter will be equals to A equals to B equals to C, and which is equal to the 6.356 angstrom. These are the fractional coordinates of this unit cell, which has created by the CIF file. And this is the CIF file corresponding to these crystal structures, and this is the Vesta file that we have generated from the software. So let's start move on the next type of the crystal. Second one is the gallium phosphide crystal. Gallium phosphide crystal structure. It is a, zinc blende type crystal structure in which gallium atom form the gallium ion form the FCC lattice and phosphide ion form present in the all alternate tetrahedral void. In alternate tetrahedral void, since it is forming the FCC, so number of gallium atom will be gallium ion will be 4 as I have calculated in first crystal. So for neutralization, there will be the 4 phosphide ion and 4 phosphide ion will be present in the void. So there are two types of the void. There are two types of the void, tetrahedral void and octahedral void. Since number of octahedral void is 4 and tetrahedral void is 8, so phosphide ion is not present in all tetrahedral void. It is present in half of the alternate tetrahedral void. So number of gallium atom is 4 and also the phosphorus ions also 4. Cell parameter for this crystal is since this is also a cubic unit cell, so cell parameter is A equals to B equals to C, and which is equal to 5.448 angstrom. This is the crystal structure. This is the gallium ion, and this is the phosphide ion, which is present in the unit cell. Void in the alternate tetrahedral void. These are the fractional coordinates corresponding to this unit cell and corresponding to this crystal. And this is the CIF file corresponding to this crystal, and this is the Vesta file corresponding to this crystal. We can open these files in the respective softwares. So now let's move on the next crystal. Third one is the potassium oxide crystal structure. This is a for anti-fluoride type structure. Anti-fluoride यानी कि Na2O type structure in which oxygen ion form the FCC lattice and potassium ion is present in all tetrahedral void. Since oxygen ion O2 minus is forming the FCC, so number of the oxygen ion will be 4. And according to this, the tetrahedral void will be equals to 8 and octahedral void will be 4. So since for one oxygen ion, we have required two potassium ion. So for 4 oxygen ions, we have required 8 potassium atoms. Since the number of potassium ion is 8, so they will goes into the tetrahedral void, which is equal to the number in the which is the same in the number. Oxygen ion per unit cell is 4 and number of potassium ion per unit cell is 8. And the cell parameter corresponding to this crystal, it is also a unit cell, cubic unit cell, so A equals to B equals to C, and which is equal to 6.449 angstrom. This is the CIF file corresponding to this crystal. This is the fraction. These are the fraction coordinates corresponding to this crystal, and this is the CIF file, and this is the Vesta file. We can also find out that coordination number ratio, since potassium ion is present in the tetrahedral void, so its coordination number is equal to will be equals to 4. Now let's move on the next crystal, which is the fourth number, cerium oxide crystal. Cerium oxide crystal structure. This is a fluoride type crystal, CaF2 type. Fluoride is CaF2 type crystal, in which cerium plus 4 ion form the FCC lattice, and oxygen 2 minus ion are present in all tetrahedral void. Since C plus 4 is forming the FCC, so the number of the cerium ion in a unit cell will be 4. And for neutralization, since we required for 1 Ce plus 1 Ce plus 4, we have required 2 oxygen ions. So for 4 Ce plus ions, we have to require 8 number of oxygen ions, since for the charge balancing. So oxygen ions will be present in all tetrahedral void. In all tetrahedral void, we can see from the crystal, this is the cerium ion which is present, which is forming the lattice, FCC lattice, which is present in the corner and face center. And oxygen ion is presenting in all tetrahedral void. This one is the oxygen ion which is present in all tetrahedral void. So number of calcium ion per unit cell is 4, and number of tellurium atom ions per unit cell will be equals to 4. We can find out the coordination number ratio, since the charge number ratio of cerium and oxygen, charge ratio is equal to 4 is to 2, or we can say 2 is to 1. And this is oxygen ion is present in tetrahedral void, so the coordination number of oxygen ion will be 4. Coordination number will be 4. So as there is a ratio in the charge, the coordination number ratio will be equal to the similar as the charge ratio. So if coordination number of oxide ion is 4, but the charge is double on the cerium ion, so coordination number will also be double, as in it will be equals to 4. So we can say from here the coordination number ratio of cerium and oxygen ion will be equals to 8 is to 4. These are the fractional coordinates corresponding to this crystal structure, and this is the CIF file, and this is the VESTA file. From we can open these files and visualize the crystal. So let's move on the next crystal. Fifth one is the gold zinc crystal. Is the gold zinc crystal, in it is a cesium chloride type crystal structures. This is the cesium chloride type structure, in which gold atom form SCC lattice, simple cubic lattice. So the gold atom will be present at 8 corners only. So number of gold atom in one unit cell will be equals to 8 into contribution is 1 by 8. So from here we can see that the gold atom in one unit cell will be equals to 1. So number of gold atoms per unit cell is 1. Similarly, for number of zinc atoms will be also equals to 1, which is present in the void and in the cubical void. Cubical void, or which is present at the body center. At body center. These are the fractional coordinates corresponding to these crystals. Gold atom is present in the cubical void, so its coordination number is 8. This is the CIF file corresponding to this crystal, and this is the VESTA file. So now let's move on the next. Okay, crystal structures are completed. Now we discuss the ferroelectric behavior of TiO3 on applying an electric field along C-axis. If we consider the ideal case of a Ti position, that Ti is exactly present at the body center of the cube, and if we apply the electric field, then position of, but actually this is slightly displaced from its original position, from its exact body center position. So if we apply the electric field, its slide starts displacing from its position as shown in the figures. It's slightly displaced and reaches to its maximum position. When we apply the electric field, as you seen in this video or in this C gift file, as we apply the electric field, this titanium ion moves upward in the direction of the electric field, but if we reverse the electric field, then it will also move in the opposite direction. If we apply the negative field, oh sorry, electric field from this direction, this will starts moving in the negative direction. So this is the hysteresis loop corresponding to this structural changes. As we increase the electric field, it reaches to a maximum. The polarization, all dipoles align in one direction, and it reaches to the maximum position, which is called as saturation polarization. But if we decreases the magnetic field, some dipoles polarization starts decreasing, and some dipoles retains, because some dipole align in opposite direction, and some there is retain some polarization, which is known as remanent polarization. And the electric field at this point, which point at we, the electric field, when the electric field is zero, the polarization is called as remanent polarization, and the electric field is known as corrosive electric field. When we decreases the when we decreases the electric field, the polarization reaches to the zero, and when the polarization becomes zero, the electric field is known as corrosive field or corrosive electric field. But if we start decreasing in the negative direction, electric field in the negative direction, all dipoles align in the opposite direction and reaches to a maximum saturation, which is known as negative saturation. And further, if we increases the electric field, as we increases the electric field in the positive direction, the polarization changes its nature, and it slightly gradually increases, and reaches to the maximum polarization. Thus, we can get the closed S-like S-shaped hysteresis loop of corresponding to this crystal. So that's all. This was the complete part B of the assignment one. So thank you. Hello everyone. Now I am presenting part C of assignment 1. In this part, we will discuss about the generation of the X-rays. So let's start. Generally, X-rays are the high energy electromagnetic radiations which have the wavelength of the order of the 1 angstrom. These are discovered by the William Roentgen in 1895 while they were performing the cathode ray tube experiment. These are produced when high energy fast moving electrons hit on the metal targets. So this is the experimental setup, the experimental instrument, which is known as the hot cathode ray tube, which is used for the generation of the X-rays. There are some parts of this instrument. There is an anode, there is a cathode. Anode is positively charged, cathode is the negatively charged. Coolant is used to maintain the temperature of the instrument. So let's start. Let's see the working principle of the generation of the X-rays. So this is the evacuated flask. This is the evacuated envelope where the anode and cathode are placed. At the anode, we placed a metal target, such as here is a tungsten metal, and we use the hot filament from where we can generate the electrons. Anode is copper rod, and it is the positive electrode, and cathode is the heated filament, is it is the negative electrode. As we apply the high voltage from the electric source, about 1000 volt source, then the filaments get heated, and the electrons are ejected from this filament. Since this is the negatively electrode and this is the positive electrode, so these ejected electrons move towards the positive electrode, towards the anode, and these high energy electrons moves towards the anode and hits to the metal target. When these high energy electrons hits to the metal target, they generate the X-rays. The X-rays, yeah, radiations, which are called the X-rays. So this is the working principle. This is the simple principle for the generation of the X-rays. When the electrons hits to the metal target, the in the generation of the X-rays, two different types of the phenomena are occur, and on the basis of these two different phenomena, two different X-rays are generated from here. So let's see what are the phenomena and what are the types of the X-rays generated from here. So first type is the continuous X-ray, a white radiation. So what happened in this during this generation of this type of the X-rays? In this, uh, since the electrons are highly energetically, electrons are heated on the metal target. So if we consider three different electrons having the different kinetic energies, if first electron, so fastly moving very high kinetic energy electron can hit if it hit directly at the nucleus of the atom of the metal target, then and change its direction and velocity, then it releases the high energy radiation, which as in the form of the X-rays. So its energy will be high and different wavelength will be, or wavelength will be less. If we consider the second electrons of the slightly lower energy, so when it hits to the metal target, it can deaccelerated by the some different other electronic interactions. It can deaccelerated by the electronic interactions, and when it decelerated, it changes its direction and its velocity and releases some radiations in the form of the X-rays. So, and having these radiations have slightly less energy than the first one. If we consider the third electron having the very less electron energy, then it will, and if this electron hit to the metal target, then it cannot reach to the nucleus or close to the nucleus. It will repel, it will deaccelerated by the outer shell electrons and get deflected or get and changes its direction and velocity, and by releasing some energy in the form of the X-rays. So from here we get the different types of the we get the X-rays having the different energies, X-rays with different energies. So we can say that the X-rays generated by this method are contains the different wavelengths, and we can say, so we these type of the X-rays, we can get a broadband corresponding to the X-rays. So this type of the X-rays we called as the white radiation, because in these radiations a high different wavelength radiations are present, so it is known as the white radiation. We can say here that the energy produced energy of the X-rays produced is dependent directly on the kinetic energy of the electrons, and we say that we know that the kinetic energy of the electron is directly proportional to the charge of the electron and voltage applied to the electron. And we know that kinetic energy is, and it is also equals to, and energy is also equals to EV equals to HSC upon lambda. So from here we can find out the wavelength of the radiations of the different radiations by this formula, E equals to Hc upon EV. So this is the formula from where we can find out the wavelength of the particular radiations corresponding to these different types of the energies of the electrons. So we can say that the wavelength of the X-ray radiations are directly proportional or dependent on the voltage. As we increases the voltage, kinetic energy of the electrons increases, and as kinetic energy increases, the energy of the wavelength increase. Sorry, energy of the X-rays increases, and as energy increases, the wavelength of the X-rays decreases. So different type of the X-rays are generated from this method, and we can find the wavelength of the radiation by this formula Hc upon Emax or Hc upon E nu. From this diagram, we can say that energy increases, the intensity of the X-rays also increases. We can say as the intense voltage increases, that means we can say that intensity of the X-rays is the function of the voltage. As we increases the voltage, here 5 kilovolt, here 15 kilovolt, the intensity, as we increases the voltage, the intensity of the X-rays increases. So now let's move on the next type of the radiation and next type of the phenomena that occur during the generation of the X-rays. is in this phenomena we can a high energy as the high energy electron comes to the towards the metal target, and as it hits to the metal target, it can collide with the electrons of the atom, outer shell electron of the atom, and it can knock out this electron and generate a vacancy. So as the vacancy is generated, the higher shell electrons, like this electron can take place this position, and when it goes from a higher energy level to lower energy level, this releases some energy, and this release energy is known as the X radiations, yeah, X rays. This energy corresponds to the wavelength, have the wavelength corresponding to the X rays. So this radiation is also known as the X radiation, yeah, or X rays. The electrons, other electrons, higher energy electrons can also be goes into the vacancy. So there it can also be released some different energy. So different type of the radiations are also radiated from this phenomenon, known as the on the basis of the generation of a vacancy, yeah, ejection of the electrons. There are two different types of the radiations form: K radiation and L radiation. If this incident electron knock out the electron of the first energy level, यानी कि K cell of K cell, first energy level or K cell, and the energy, the electrons of the higher energy comes into the this vacancy or generated in the K cell, then the energy released, yeah, radiation released during this transition is known as the K radiation. This transition, the radiation corresponding to this transition is known as the K radiation. But if the ejected electron hit to the second cell electron and create a vacancy by knocking out this, then and the higher cell electrons, as here we can say this electron comes into the vacant site or vacancy, then this type and release, and when it goes into the it go to the lower cell, it release some energies, and this radiation is known as the L radiation, because the vacancy is generated in the L cell, or transition of the higher cell to lower cell is taking from higher cell to L cell. So this is known as the L radiation, and this is known as the K radiation. There are also different types of the L radiations and K radiations, as K alpha, K beta, K gamma, as K alpha, K beta, and K gamma. So what are these? So let's understand what are these. If the ejected electrons knock out the electron from the K shell, then this will be the radiation of the K radiation. And if the electrons of the second cell comes into the first cell in the K cell where the vacancy is generated, then it is known as the K alpha. And if the an electrons transition takes place from third energy level to the K energy level, then this is known as the K beta. And if the electrons from the fourth energy level is taking from fourth energy level to the K level where the vacancy is generated, then this transition is known as the K gamma. Similarly, if the incident electron knock out the electrons present in the second cell, this is the L cell, and create a vacancy, and the higher energy level, that means the third energy level electron goes into the vacancy, then the radiation generated is known as the L alpha. And the if the electrons goes into into the vacancy from fourth energy level to second energy level, then this is known will be known as the L beta radiation. So these are the different types of the radiations which are generated from the transitions of higher energy level to the lower energy levels. We can find out the wavelength of the characteristic, since there is only one type of the transition can take at a particular time. So we called it as a characteristic wavelength. Or since the here the transition of electrons is not affected by the voltage applied, it can affect only by the metal target. it can affect only by the metal target. So we can say that the radiations generated by this method are known as the characteristic radiation or characteristic, and the wavelength corresponding to these radiations are known as the characteristic wavelength, because it is the it is dependent on the metal target. Now let's move further. So, as we earlier said that white radiation, the energy of the white radiation, yeah, intensity of the white radiation is dependent on the voltage. As voltage increases, the intensity of the white radiation increases. But as I earlier said that the radiation intensity of the characteristic radiation not depend on the voltage. It is only depend on the metal target. It is only depend on the metal target. Means we can say that it is the characteristic property of the metal, not of the voltage. From the diagram we can say as the voltage increases, the wavelength of the intensity of the white radiation increases, but there is no effect of the voltage on the K alpha and K beta, means characteristic radiation. There is no effect on the characteristic radiations. So let's move further. X-ray absorption. Since here two different types of the radiations are formed, K alpha and K beta. So we have to differentiate, or we have to use, if we have to use a particular type of the radiation, so we have to require to separate, to filter these radiations from each other. So we use this phenomena which is known as the X-ray absorption. X-ray absorption is used for the filtration of the monochromatic radiation from the different type of the radiations. In the X-ray absorption, X-ray photons are absorbed by the atoms, causing the excitation or ejection of the inner shell electrons. Means for this phenomenon, we use a sheet of the atoms. We use a sheet of the substance which absorb the radiations of a particular type. If we we want to differentiate between K alpha and K beta, then we use such like a sheet of atoms which can absorb the K beta radiation very strongly, but K alpha at very low cost, at very low frequency, या at very low, मतलब के बीटा को 100% एब्जॉर्ब कर ले और 99% एब्जॉर्ब कर ले, बट अल्फा रेडिएशन को या के अल्फा रेडिएशन को वो बहुत ही कम एब्जॉर्ब कर पाए. तो वी यूज such like of atoms, sheet of atom, a sheet of substance to differentiate between K alpha and K beta radiation. So from here we can say as the wavelength increases, the absorption increases, because as the wavelength increases, the energy decreases. Energy decreases. As energy decreases, so absorption by the atoms increases. Absorption by the atom increases. Absorption by the atoms increases. Or we can say reversely, as if we decreases the wavelength, energy increases, and as energy increases, absorption decreases. This absorption decreases. But if we further decrease the wavelengths, if we further decrease the wavelength, the energy is highly increased. Energy is highly increased. So now this energy is sufficient for the ejection of the electron, for the ejection of electrons from a particular cell, K shell or L cell. At this point, the absorption increases sharply because the ejected electrons is absorbing the energy very high at a very very sharply. So is this point is known as the absorption age or K absorption age. And if we further increase the energy, the electrons gets ejected and the absorption further decreases. From here we can say that as the lambda increases, energy decreases, and as energy decreases, absorption increases. Absorption increases. Or reversibly, we can say that as lambda decreases, energy increases, and as energy increases, the absorption decreases. Absorption decreases. So now let's move further. The synchrotron. Synchrotron, what is the synchrotron? Synchrotron is also a X-ray generator. Synchrotron is also a instrument from where we generate the X-rays. Synchrotron is a instrument. Synchrotron is a large evacuated circular particle accelerator. ये क्या होता है? एक एक्सीलरेटर है. It is a particle accelerator, charge particle accelerator, having the diameter of the tens to the hundreds of the meters, and it's a very large circular accelerator. इसका diameter, its diameter is about tens to hundreds of the meters. It speeds up the electrons or other charged particles nearly to the speed of the. It is used to generate the X-rays. When the electrons are introduced into this, then this is the internal structure of this synchrotron, because it is the highly magnetized. So as the electrons comes in in the synchrotron, then it's get deflected by the magnetic force, and it by changing its value, since the direction and velocity is changing by the magnetic force, so its velocity is continuously increases and it gets accelerated very high speed. And as these electrons gets accelerated at very high speed equal to the light speed of the light, then these electrons radiate X-rays. These electrons radiate the X-rays. So as the electrons kinetic energy increases, then they radiate the X-rays. When the electrons are accelerated, they emit the light radiations, and when the speed of the electron becomes close to the speed of the light, accelerated electrons emits the X-rays. But since the electrons kinetic energy is continuously increases, so the electrons emit the X-rays of the different wavelengths. X-rays of the different wavelengths. X-ray of different wavelength. That means we can say different wavelength. So from here we can say that the X-rays generated from the synchrotron uh, will be white radiation type. Will be white radiation, not the characteristic radiation. So this is all about the synchrotron and the synchrotron radiations, or the X-rays generated by the synchrotron. So let's move further. So this is all about the part C assignment which has completed. So thank you.